Hello and welcome back to chapter 3 of this information hiding class, and today I will discuss fundamental countermeasures, i.e. countermeasures that are not specific to network steganography or network covert channels, because I will deal with them in a separate chapter. This chapter here is the final chapter of the fundamentals. After we covered these fundamentals, chapter 4 will start with the network specific aspects. We will then first cover the hiding techniques and patterns, and then sophisticated hiding methods, and then network level countermeasures, and then there will be some chapters that will deepen your knowledge, like chapters that have to do with experimenting in the domain or writing papers in the domain. And in the end, we will cover IoT steganography. But for today, we need some better solid ground, some foundation for the chapters that will come. And so we will have a look at these fundamental countermeasures. So the first approach that I want to highlight is the shared resource matrix methodology developed by Camera. And it's an approach to detect covert channels that are storage channels, i.e. those that do not signal information via timing events, but by writing to some storage location and then reading from this storage location. So the covert sender sends some message to the storage or some data to the storage location, and the recipient, the covert receiver, tries to determine the content of this message stored in this shared resource. This SRM, shared resource matrix methodology, is SRM in short, can be applied to different steps of the software development lifecycle. Even if you have a very early stage of the software development lifecycle, so you start with some textual specification of the software and it's not even there yet, there's also no prototype or something like that available, then you can still analyze the textual specification using the SRM, but you can also apply it directly to source code. John McHugh later improved this work, I think in 1996 or so, but we focus only on the original version by Camera. The general assumption here is that a system can be described by operations and attributes, where the operations have a link to the attributes. And the goal of the SRM is to determine whether an operation X can modify an attribute A under the condition that operation Y, which is a different operation, can read the attribute A. So an example can be seen below. I have a table here. We have different operations: read, write, delete, and create. And let's assume it's something related to the file system here. We have file existence, file owner, file name, file size. And so the read operation can read the existence of the file. Because if you try to read the file and the file does not exist, then you get some error returned. And if you read the file and it exists, well, then you get the data. So you can determine the existence of the file. Same for file name and file size. Maybe it can also view the file owner, but it depends on the implementation of the read function. Usually it does not determine the file owner, and in many cases also not the file name, but we have to agree on some setup here. The write operation would be able to read the file existence, because if you write to a file and the file does not exist, well, then it's difficult to write to the file, actually impossible unless the file is automatically created. It can also read the file name, and it can modify, that's the M here, the file size. And this works a similar way for delete and create options. So what we need is one option operation used by the covert sender to modify an attribute, and the other option used by the covert receiver to read the attribute. For instance, using create and delete, we could create a file, or simply we could not create a file to send a binary 0 or 1. And we could then read the file to determine its existence. And if we do not need the file anymore because we want to signal another binary value, then we use the delete option to remove the file. However, a simple channel could also be one that just transfers one bit by creating the file once or not creating the file. There are some problems. Some covert channels can be false positives. For instance, if two operations could build such a link where one operation modifies and the other reads the attribute, but if these operations cannot be called by two different processes using different security levels, or in general in a way that the security policy is not violated, then it's simply no covert channel. And the SRM supports no sequences of operations, but a sequence of n operations maybe lead to an indirect recognition of a modified attribute. Camera states that all storage and all timing channels can be detected using the SRM. However, Bishop stated in his book that this is wrong. Another approach are covert flow trees. They were introduced by Camera and Porras in 1991. And so the idea here is instead of having, like we had it with the SRM, a method to automatically detect covert storage channels in source code. I will cover this approach only briefly. In the original paper you find much more information about this, but this is about the core concept of the authors. So let us assume we have the following code. We have here one procedure, increase temperature, that heats something, takes some current temperature value, and then increments the internal temperature. Let's say it heats until 1 more degree is reached, and then the internal temperature is set to incremented by 1. And we have the procedure check temperature. And if the internal temperature value is within some soft limit, then we return the temperature, otherwise we return some error code. Some code that maybe represents a state that is telling us that we ran out of some soft limit. Of course, no good engineer would write such a code, but it's just for demonstrating the purpose and the functioning of the covert flow trees here. So what we do is we again create some kind of a matrix with the operations or procedures here, increase temperature and check temperature, and we write down which attributes are referenced, modified, and returned. For instance, the increase temperature procedure references current temperature and internal temperature. It modifies internal temperature. It does not return anything. The check temperature procedure references internal temperature and the soft limit, and it modifies nothing, but it returns the value of internal temperature. at least under some condition. Otherwise, it returns 999. Based on this table, on this matrix, we create, or actually this is done all automatically, the covered flow tree for each attribute. In the original paper, I don't paste the original paper's content here and the figures because it's IEEE content and I cannot just copy and paste the figures here. So unfortunately, I had to redraw things and I simplified this, but you see actual source code output and you can also see covert flow trees, and you will also see that they become much bigger than I visualize it here. But the core idea is you select an attribute like internal temperature, and you have logical conditions, logical ORs, and logical ANDs. In this case, if you want to establish a covert storage channel, you need to have both a modification of the attribute internal temperature and a recognition of the attribute internal temperature. Only if both is available, you can establish the covert channel. There's a direct modification of increased temperature feasible via the of internal temperature feasible via the increased temperature procedure, and we see this because it is here visible under modify and if we want to recognize the modification of the attribute internal temperature, then we can also directly recognize this using the return value of the check temperature procedure. Indeed, there's more to say about covert flow trees. There are also indirect channels feasible. Let's say we can indirectly, because there are some operations that are influenced by internal temperature and some other return value is then calculated based on that, and we indirectly have a recognition of the value using some other procedure. That's also feasible. And then we would have a logical OR here because we just need to fulfill one condition. Anyway, I don't go into this detail. The next thing here is we take the tree and build two lists. List 1 contains operations capable of modifying the attribute, which is increased temperature here. And the list 2 contains operations capable of reading the attribute, which is check temperature and some other procedure. Finally, we combine the two lists elements. So we start with increased temperature to modify the attribute, and then we use check temperature, first element of the second list, to recognize the modification. In the same way, we use increased temperature with some other procedure to indirectly recognize the modification. Whatever this method or procedure does, we don't know. Oh yeah, and the indirect recognized procedures also land here in the list 2. Covert flow trees can be applied at the source code level. That's a drawback in comparison to the SRM because we are limited to the source code level. However, they work automatically, and this is pretty good. I don't think that there's a current implementation available for modern programming languages, but it works, and one can potentially port this to modern programming languages. Nobody has published work on timing channel detection using covert flow trees so far. So we assume that covert flow trees can only be applied to detect covert storage channel, unless the opposite is proven. Another advantage is the visual representation of the flows that eases the work with such a system. And also a plus is that covert flow trees support indirect information flows. Fuzzy time is a completely different approach and was published by WHO during the IEEE Security and Privacy Symposium in 1991. One needs to understand that back then virtualized operating system environments were already known. The VEX security kernel was capable of handling such virtualization environments. So you could have different virtual machines running on your system. And that was long before the cloud era began. And the idea here is, in comparison to the shared resource matrix methodology and the covert flow trees, to detect covert timing, or actually to limit covert timing channels. It's not a detection and not a prevention approach, but it limits the channel capacity of covert timing channels. So the idea is here that there are two isolated virtual machines, and the assumption is that they cannot communicate directly with each other. However, if they exploit some hardware capabilities like software-based interrupts, then they could influence the VEX security kernel, and the VEX security kernel might forward or inform all virtual machines of some hardware or soft interrupts. And in the end, the point here is that these interrupts could be exploited to represent covert timing information just by influencing the timing of events. And the more precise the timing measurements are, the more bits can be transferred per unit of time. So the idea here is, let's suppose we have 3 events, E1, E2, and E3, that occur at different times, called the event time or downticks. And the event time is the actual event timing where the event occurs, while there is a randomized delay to inform the virtual machines. So event E1 that occurs at event time here is not directly forwarded to all virtual machines. Actually, every virtual machine gets an own time delay, an own randomized time delay. But virtual machine 1, let's say, gets the notification at N1. And these notification times are called upticks. And maybe between E2 and N2, there's a larger time gap, while between E3 and N3, it might be very small. So it's not so easily foreseeable. And in the end, this makes timing measurements of the virtualized machines less precise, reducing as a consequence the covert timing channel capacity. Finally, I will show you one approach that also limits the capacity of such channels. It's called the Spurious Processes approach by Fadlallah. I think it's a rather unknown approach, but when I was a PhD student, I read his thesis. It's actually an approach to prevent such channels in databases, but I explain it using file system based storage channels. So the basic idea here is that the operating system kernel would introduce a spurious process called SP here into all potentially covert communications between two regular processes of an operating environment. This limits the capacity of the storage channels, and the spurious process is introduced on context switch if a shared object is accessed by two processes without previously having the spurious process accessing the same object. And the spurious process always operates with the same permissions as the following process. So, for instance, an example could be that two processes in a multi-level security system would communicate over unique file names, while P2 calls the create syscall to determine whether P1 already created the file, because P2's create will fail if the create was successful, and it will be successful if P1 did not create the file. So let's have a look at the table here on the right side. P1's behavior is on the left side. In the middle we see that P1 creates the file or does not create the file. And so let's assume it signals a hidden 0 bit when the file is created and a hidden 1 bit if the file is not created. So the idea here is that the covert receiver process would now be called, get some computation time, and would like to access the same resource, namely the file that P1 created or did not create. And because of that, the operating system would introduce now the spurious process. So if the spurious process runs with the same permission as P2, then creating the file would not work here because first of all, the file was created by P1. And if the file is then removed, this would also not work because P2 has lower permissions than P1. P2 cannot create delete files that P1 created. So in result, the file would still exist because in the write down, the spurious process lacks the rights to create the file. And P1, what would P1 receive? It would receive the 1 bit, but it would be unsure whether the SP or the spurious process created the file if the file was not created by P1 but created by the spurious process, because in the end the file would exist. So P2 cannot be certain regarding the result. However, it can be certain in case P1 did not create the file and the spurious process created and removed the file, because in the end, in both cases, the file does not exist. So a 0 bit can be transferred in this case. However, it could be the case that the file was not created and it's only existing because the spurious process created the file. So this reduces the information that P2 receives quite a lot. So as you can see, this approach works somehow, but as one can imagine, if a spurious process really disrupts process interactions like done here, it can cause several failures in the system because many processes are not implemented in a perfect way. That means the error handling is not bulletproof, and so such a spurious process might break some process behavior. All right, that's all for the fundamental countermeasures. You have now basic understanding of such countermeasures, how different they can be, how they can work. And by the way, we developed such a spurious process approach for our Android covert channels that I presented in the last chapter. You find idea realized in the paper that I linked in the chapter that we covered last time. And so it can be done, but it always has some drawbacks. It's far from being a perfect approach, but interesting to know, and it might be possible to improve the approach further and apply it to modern systems in a way that the side effects can be realized. But that's enough for this topic. We will focus next time on the first techniques used for network information hiding.